formula good for? When do you use it? What does it say? Tell me everything that formula, what's the information that's being conveyed by this formula? Would someone like to tell us?
Force is perpendicular to velocity and magnetic field.
Oh.
So it's a force on what? Exerted on what? By what?
Force on a chart.
It's a force exerted on a charge when it's exerted magnetic field.
That is moving.
That's moving.
And the charge is moving, right, with velocity v, and q is the charge. So it's a point charge.
Can't be neutral.
Just before we get started, on Doral, like the actual questions are missing.
I think it's fixed.
It's fixed now?
I think I checked before class.
I checked for class.
It
What
has,
did
like,
you
it has
last
the
check?
image and then it's asking for the magnitude.
Like the answer, but like where it asks for the answer, there's just like the part A question, but the overall
It just got
question
it.
is not there.
It's on there now.
It's on there
It's
now?
on there.
Okay, yeah, never mind, sorry.
I checked like
And I
right.
didn't say anything.
Right
They
before-
probably, I wrote it, selected some questions yesterday, and then I wrote the people, and I told them, hey, could you check this? But I don't expect them to check their work email on Sundays, so they probably did it today. But if you review the problems that I solved from the textbook for which there are solutions, that's should be enough. So this is the force experienced by what? By a charge q. A charge q that what? That moves with velocity v. And moves with velocity v where? In a region where there is a magnetic field there already. And this will be the force. It's not going to be zero as long as the charged particle doesn't move in the same direction as the magnetic field or the opposite direction as the magnetic field, right? So the particle has to be charged, it has to be moving in a region of space where there is a magnetic field, but as long as it doesn't move in the same or opposite direction as the magnetic field, right? So it's the force on a point charge exerted by an external magnetic field. I call it external because it is not the magnetic field generated by the point charge. Right? I think we talked about that last time. Well, hold on, it's supposed to be 27 and 28. Now, what happens if there's a wire and the length of the wire is L? Maybe there's a wire and the length of the wire is L and the wire has a current in it. Maybe the current is this way or maybe the current is that way. And what if I place this wire with this current I in it, length L? What if I put it in a magnetic field region? What will the magnetic field do to it? It will exert a force. So what will the force that the magnetic field generated by some moving charges somewhere else? So I'm not interested in that part. What will be the force that the magnetic field will exert on that wire of length L when the wire has this current and it is placed in an external magnetic field? Then the force is going to be given by this. Now, can you tell me all cases when that force on the wire is going to be zero?
When current and the magnetic field run parallel.
When the current in the wire is in the same direction as the magnetic field. So for example, if the magnetic field is given by, let's say the magnetic field is pointing up this room, everywhere, pointing up. Suppose the magnetic field is pointing straight up. And I do have a wire with current in it, and the wire is vertical. So if the current is in the same up the wire, in the same direction as the magnetic field, this magnetic field is not going to do anything to the wire. It will experience zero force. Or what happens if the current is in the opposite, down the wire, with the wire being vertical in the same direction as the magnetic field, but the current is in the opposite direction to the magnetic field, the cross product is still going to be zero. So if the wire is vertical to the magnetic field, it will not experience a force. Or what happens if the wire is there, but the wire doesn't have a current? If the wire doesn't have a current, there's not going to be a force on the wire. Right? What happens if the wire is there and there is a current in it, but there is no magnetic field in that region that can exert the force on the wire? Then, if there's no magnetic field, there's not going to be a force on the wire either. So, this is the expression for the force exerted by an external magnetic field on a straight wire of length L when the wire has a current I in it. And this force is not going to be zero as long as this current is not in the same direction or in the opposite direction as the magnetic field that it's sitting in. Right, so that's the message there. In fact, let me apply this expression to a problem. Let me make up a problem. What if we have a, let me just apply that formula to the following case. What if there is a very long wire and the current in it is 10 amps. All right, very long. And there is a loop that has a current in it. Let's not worry how that current is generated, but let's say that there is a square loop placed in there, or rectangular loop placed in here on the plane of the board, right? So there's a loop like this. That's supposed to be straight. And suppose this loop has a current in it. Which direction would you, let's make this length 2 meters. So this would be 2 meters. Let's make this 1 meter. Let's make this 1 meter. Would you like the current to be in the clockwise or counterclockwise sense? I'll let Mary choose.
Clockwise?
Clockwise. So let's make the current. How about I make it 5 amps? Right, it'll be this way. On this segment is going to be 5 amps up. On this segment, it'll be 5 amps to the right. So the question is this: what is the net force exerted? Let's call this wire number 1, and let's call this a loop. Exerted by wire number 1 on the rectangular loop. So the current in this wire number 1, the one that's very long and straight, will generate a magnetic field over there, right, where this rectangular wire is, and that magnetic field will exert a force on this loop, on this rectangular loop. What is the net force on this loop exerted by the current in this very long straight wire? So what I can do is the following. I can say, well, this vertical segment over here, I'm going to call it segment number 1. That one I'm going to call it segment number 2. This one I'm going to call it segment number 3. And this one I'm going to call it segment number 4. So let's consider segment number 1. I want the force on this segment, right? From here to here. What's the force on it? So, it will be, the force of segment number 1 will be the length of segment number 1, right? I'm using this formula. Correct? It'll be the length of segment number 1 times the current in segment number 1. I'll call it just I1. Times the magnetic field there, the magnetic field at the location of this segment. But who's producing that magnetic field? wire number 1, right? It's producing a magnetic field there. Right? And now that you have prepared for this quiz, it should be easy for you to figure out what is the magnetic field over here. Right? Let's call it B1, generated by this current in this wire. So how about I say B at segment 1 due to wire number 1. So let's see, this will be, the length of that segment is what, 2 meters? I1, what is the current in this segment of the wire? It's 5 amps up, right? 5 amps. And I'll say up, cross into. What is the magnetic field at this location? Due to this wire. It would be which way?
Out of the board.
Which way?
No, into the roof.
Into the board. And how big? It's a long wire, so it would be mu naught times the 10 amps divided by 2 pi. And what is this distance? Oh, I didn't give a distance, right? So let me make this distance. How about I make this distance 4 meters? Divided by 4. And which way is that magnetic field pointing? At the location of segment number 1.
Into the board.
Into. Are you guys with me? Yes? No? Maybe?
Yes.
Right? This is the length of the wire that's experiencing the force. So segment number 1, I made it 2 meters long, right? I is the current in that wire that experiences the force. Well, I made it 5 amps, 5 amps, 5 amps, 5 amps, clockwise, right? But in this segment, it's 5 amps up. So 5 amps up the page, up the board over here, 5 amps up. And then this magnetic field is the magnetic field that this loop is exposed to. And this loop is exposed to the magnetic field generated by the current in this wire. And this is just a very long wire. Its magnetic field is mu naught I over 2 pi r. So mu naught times the current in the long wire, which is 10, divided by 2 pi, and I made r equals to 4. And since this wire has a current going up, it will generate a magnetic field pointing into the board. So now, this would be 2 times 5 is 10. Times 10 is 100. It would be 100 mu naught divided by 8 pi. Now, in which direction? In the direction of up, cross, into. So what is the cross product of up, cross, into? Into is into, up. Like red cross blue. To the left. Okay, so this here will be,
Give it to my hand.
in other words, is being attracted by the long wire, right?
For this one.
So you work this out, right? And this would be 100. Mu naught is 4 pi times 10 to the minus 7 divided by 8 pi, and this is to the left. So this would be what? I can see that this cancels that. That gives me a 2. So that's 50. 100 divided by 2 is 50. 50 times 10 to the minus 7 would be 5 times 10 to the minus 6 Tesla to the left. That's the force on that segment. Newtons. Thank you. Newtons. Sorry, Newton. So the force on segment number 1 is going to be this way. 5 micronewtons. Maybe I should write bigger. Good? Now, for segments 2 and 4, see, the distance is going to be changing, right? So the force is going to be changing. But we can notice something. What will be the direction of the force on segment number 2, excited by this magnetic field, generated by this wire? This wire generates a magnetic field, let's say, over here, pointing which way? Into, right? So I'll be like an X, into. So B is into. But the current is to the right. So what is the direction of I cross B? What is the direction of to the right cross with into? Up, right? So the force on this segment is going to be up. But if I consider this segment, what is the direction of the magnetic field here generated by the current in this wire? It's still into, right? But now the current is this way, to the left, in that segment, right? And what is the direction of I cross B?
Yeah.
So I cross B will be down. So the force on this segment is going to be down. So if I consider the same distance from here to here as from here to here, this will cancel this. If I consider another segment over here, the force is going to be smaller, but if I go over there, it's going to be smaller also, but it's the same distance, so this is going to cancel this. So the forces on segments 2 and 4 cancel out completely. Do you see that? Yes.
Could you explain how up cross into is the left again?
It's because your fingers
So-
go high.
First vector is your 4 fingers of your right hand, straight. Second vector into.
Would that be pointed to the right?
No, your palm. Your palm is into.
Like this.
You
So
feed
the
your
second
palm
vector is your
up.
palm, not your thumb. So the first fingers, the 4 fingers is the first vector which is up, and your palm is into, like the way you have it right now.
Right. Okay.
And then the thumb is to the left. That's
So
the
like-
thumb is a cross product.
So like your fingers are right and your palm is into the force, so your thumb is going to be facing up.
Yes. I was thinking of it the other way.
Yeah.
Oh, no, palm is
Your
up.
fingers are based off of the first number in the cross.
So 4 fingers, palm, the answer is the thumb.
Is the answer.
Right? 4 fingers up, the magnetic field into the page or into the board, and the thumb is to the left. Yeah?
So if it was out, if it was up cross out, it would be to the right.
Yes, exactly that, like that. So up, that would be the 4 fingers, out would be your palm, and then the force is gonna be to the right. Correct. Which is what's gonna happen, so were you able to follow that the force on segment 4 and 2 will cancel each other out?
Yes.
What about the force of segment number 3? Let me do that over here. So the force on segment number 3 will be the length of wire number 3, well, not the length of the segment number 3 is what I should say, times the current in that segment, which is I3, right? I'll write it like that, cross, and then the magnetic field there, at 3 due to the long wire number 1. So this would be, what is the length of segment number 3? Just 2 meters, right? What is the current in segment number 3? 5 down the board, right? Cross into. Now, what is the magnetic field? What's the magnetic field here? Due to the current in this wire, right? So the current is up, so over there, my fingers are gonna be into the board. So the magnetic field here would be mu naught times 10 amps divided by 2 pi, and now what is this r? It looks like it's gonna be 5, right? And it's into the board, right? So this would be, I'll write it out, mu naught times 10 over 2 pi, the distance is 5, and this would be into the board. So this force on segment number 3 will be 2 times 5 is 10, 10 times 10 is 100, so that would be 100 divided by 10 pi, and then we have mu naught. I'll just write mu naught like that. And what is the direction of down the board cross into? So what is the direction of the cross product of down cross with into? Which one?
Right.
To the right, correct. And 100 divided by 10 is going to be 10 divided by pi. Mu naught is 4 pi times 10 to the minus 7, right? And this is to the right. Did I write 4 pi times 10 to the minus 7 here? Yes, I did, right? So the pi's cancel. 4 times 10 is 40. 40 times 10 to the minus 7 will be 4 times 10 to the minus 6 newtons to the right. So this segment will experience number 3 will experience a force of 4 micronewtons to the right. So the forces on the 2 horizontal segments, 2 and 4, will cancel out. The force on this segment that's vertical on the left will be 5 to the left, while this one will be 4 to the right. What's going to be the net force?
1 to the left. 1 times
1
10 to the
left,
negative 6.
1 micronewton to the left. So therefore, it's like the net force equals the force on segment number 1 plus the force on segment number 2 plus the force on segment number 3 plus the force on segment number 4. So we said that 2 and 4 cancel, and then the force on segment number 1 is 5 micronewtons to the left, added to this other vector on segment number 3, which is 4 micronewtons to the right. Well, 5 to the left and 4 to the right is 1 micronewton to the left. In other words, it's going to be attracted by the long wire. That's like an application of this problem, right? I mean, of that formula. Can I do this slightly differently? Just slightly differently? Can I erase this part over here? Or does anyone have a question on this before I erase it? Yes?
So, how do you decide the B on 2 and for 2 and 4, the magnetic field?
So the magnetic field will be, it will be mu naught times this I, which is 10 amps, right? Divided by 2 pi, and then R, where R is, if I want that point, it will be this R. And that's into the page, right?
And the direction. Get the direction.
So, well, the current in this segment is to the right. So the current for that segment is to the right, and the magnetic field is into. Right? This one generates a magnetic field pointing into the plate. Actually, everywhere to the right of this on that plane, the magnetic field is into. So if the current is to the right and the magnetic field is into, so the current is to the right and the magnetic field is into, what is the direction of I cross B? I cross B. 4 fingers, palm. Right hand. 4 fingers, palm. So 4 fingers, first vector, palm, thumb, the force is up. Now, over here, the magnetic field is still into, right? But the current, see, the current here is to the right, but when it gets over here, the current is to the left. So in that case, the current is to the left, but the magnetic field is still into the plate. So what is I cross B? That will be down. And if I go to the same distance, R, like at that point, right? So the same distance, R, right? This force is going to be exactly the same as that force, except opposite directions, they'll cancel. Now, this force is to the left, this force is to the right. They tend to cancel, but they don't cancel completely because the magnitudes are different. This one experiences a bigger force compared to that one. So 5 doesn't cancel 4. You know, if this were 5 and this were 5, then they will cancel completely. 5 minus 5 would be 0, right? But you have 5 minus 4. But over this segment, right, if I go to the same distance, right, same distance, like this force is gonna be smaller than that because it's farther away. But if I go over here, it will be the same force, smaller than this because it is farther away, but this is still gonna be opposite to that, so they'll still cancel. Yes? So, see, right, so what if you have the following? An object with mass m1 and another object with mass m2, let's say separated by a distance d. Do they attract or do they repel? Just 2 objects with masses.
They attract.
Right? So the force is going to be attractive. And we call this the force of gravity, right? Same magnitude, right? So this is, gravity, right? Or gravitational force. What will be the magnitude of that force? Do you remember? But the minus means what? Attractive. So what's the magnitude of the force? Good. So capital G, like she said, times m1 times m2 divided by
R squared.
which is, I called it D, right?
Or wait, oh.
I called it D, the separation between them. R is D,
Oh, yeah.
right? Okay. Number 2. What about an electric force? That would be when you have point charge here and another point charge there, separated by a distance d. Right? What is the magnitude of that gravitational force? Sorry, electric force. What's the magnitude of it? So what should I write down? These are point charges. Okay, Q1, Q2 over d squared, right? I'm sorry, yeah, K, Q1, Q2 over D squared, that's the magnitude. Now, because the charges can have two algebraic signs, positive or negative, the force could be attractive or repulsive. If they're equal in sign, plus plus, minus minus, they'll repel, and the forces will be this way, right? But if one of them is positive, the other one is negative, then they'll attract. So I'll just, let's make them plus, minus, so that they attract. But they could also repel, depending on the signs, right? In fact, how about I make them both plus, so with different colors? Then in that case, it will be the same magnitude of the force, but it will be a repulsive force. So that's when you have a magnetic force, right? Sorry, gravitational force there, electrical force over here. Let's now consider a magnetic force. And let's consider not two charges, because there are no magnetic charges, right? How about we consider two currents? How about we consider a wire, right? Very long wire with current I1, and another wire that's very long but parallel to it with current I2, and the distance between them is D. And the direction of the force that one wire experiences will depend on the relative directions of the two currents. So suppose I make the current I1 point up in this wire to the left. Choose one for this one. What would you like me to choose for I2? Up or down?
Down.
Down. Okay, so let's make it down. So let me erase this, and let me just calculate that force that one wire exerts on the other one. And then the other one will exert the same force in magnitude opposite direction on the first one. So let me calculate the force on wire number 2. That will be this one here, right? What will be the force, the magnetic force, that wire number 1 will exert on wire number 2? Well, according to this expression, I want the force on wire number 2. So this will be the length of wire number 2. This is the current in the wire that experiences the force. So it will be the current in wire number 2. So I want the force of wire number 2. In fact, let me write down the question. What is the magnetic force on wire number 2 exerted by the other wire, right? By wire number 1. So the current on wire number 2 is I2 down the board. I'll just write it like this. I2 down. Cross into. Then I need the magnetic field that wire number 2 is sitting in. But who generates that magnetic field at the location of wire number 2? It's the current in wire number 1. So in this picture, what is the magnetic field that the current I1 in wire number 1 exerts on wire number 2? What should I write down?
Mu naught I1 divided by 2 pi d.
Exactly. Which way?
Into the board.
Good. So what will be the force on wire number 2, or with current I2? It will be the length of that wire. There's a mu naught in there. I multiply the magnitudes of the two currents, right? And in the denominator, I have a 2 pi d. And this will be in the direction of, in this particular case, in the direction of down, cross, into. So what is the direction of down, cross, into? Down, down, first vector for fingers, cross, into. Palm into the board. It will be?
Sorry.
To the right. So this is to the right. So the force on wire 2 will be L2 mu naught I1 I2 over 2 pi d, and this will be to the right. In other words, they will repel each other. So what I would write down over here, normally, and this wires, by the way, notice that I use this expression, right? If I use this expression, I'm saying that wire number 1 is very long, right? Like an infinitely long wire. So normally, you express the force per unit length on wire number 2. So it would be the magnetic force per unit length. So this is just the magnitude. Will be what? Mu naught. And then you multiply the two currents. And then you have a 2 pi d. Now, notice the interesting case over here. Remember that if the charges are opposite, plus minus minus plus, do the charges attract or repel via the electrical force? Do they attract or repel when the charges are opposite in sign? Attract, right? What happens when two wires are parallel and they have currents in opposite directions? Do they attract or do they repel? What did we say? If the force is to the right on wire number 2, then the force on this one is this way.
Oh, current and opposite.
So it's actually backwards of this. Here, opposites for the electrical force attract. But here, opposite directions of current, if you want to think of, oh, they're opposite. Oh, I think they should attract. No, then switch it. They repel. So when you go back to this problem here, if you look at this wire and segment number 1, what was the direction of the current in segment number 1? Up, right? Same direction, you would think they repel, but it's the opposite of the rule for the electrical force. So they attract. And when you consider this wire with this other one that has the current in the other direction, right? They're in opposite directions. You would think that because of opposite they attract. No, but for the magnetic force they repel. And because this wire is farther away from this one, the force, the magnitude has to be weaker, has to be smaller, right? Because it is sitting in a smaller magnetic field generated by this wire, so the force will be smaller. That's why if this is 5 micronewtons to the left, this one has to be less than 5, because it is farther away. The force is going to be less. But, you know, I just wanted to put this in perspective if you wanted to think of it in terms of, you know, what is the force that one thing exerts on the other one. For gravitational forces, right, this force, this equation was given to us by Newton. He said there's a constant, and then you multiply the two masses and you divide by the separation squared. Right? Coulomb gave us this other one. If you have two charges, right, then the magnitude of the electrical force is a constant. It's just a different constant, right? It's a different type of force, right? And then here you multiply the two charges together, and then you divide by the distance squared. So that force goes as a distance squared, this one goes as a distance squared. Now, for magnetic forces exerted by one wire with current and another wire with current, and they're in parallel like this, parallel, the wires are parallel so that the currents are in the same or opposite directions, then the force per unit length is what you calculate over here, right, is a constant, and then you multiply the two currents. Notice that in order for one wire to exert a force on the other wire, both wires need to have current in them. This one to generate the magnetic field, and the other one, you know, it has to have a current in the presence of the magnetic field of the first. So both of them need to have current, just as both of these need to have charges, just as both of those need to have masses. And then you divide by, well, it goes as 1 over d, not 1 over d squared. So if you know this expression, this problem you can do very quickly. This one is attracted by this, right? And we said that this current was going to be clockwise in this loop because Mary chose it like that. Right? If she had said counterclockwise, then this current here would have been down, with this one up, so they would repel. and this one being up, and this one up, they would attract, but this would be weaker than this, so the whole square loop is going to be repelled by this wire. But, you know, the common mistakes that people make when they write down an equation like this or an equation like this is they don't know whose magnetic field that is. They think that that magnetic field is generated by this current, and, you know, it creates confusion, right? They think this is it, you know, so you have to understand what each term means. This is a magnetic field. Who generates that? This is a current. A current where? Is it the one that generates the magnetic field, or is it the one, the current and the thing that you calculated the force on, right? This is a length. Well, whose length? Like in this picture over here, well, whose length is it? Is it the one that's creating the magnetic field, or is it the one that's experiencing the magnetic force? Right? So it has to be clear to you what each term in the formula means. And then there's a cross product in there, which, you know, as you can see, it's very important to be familiar with. Good? Okay, so now I would like to consider, we have like 45 minutes, right?
Mm-hmm.
So now I would like to consider the following.